All right, good afternoon, everyone. So today might be the most important lecture of the semester. Stuff we're talking about is super fundamental. It is a little bit intricate. You have to pay attention. I'll try to guide you through it. So last time we started by talking about random variables. So random variables are these weird mathematical entities that you kind of think of like a big bag of marbles, where you pull values out of the bag, you pull marbles out, and the marble has a number printed on it. But the random variable is like the entire bag itself. It's not like just a single marble. It tells you all the possibilities and how often they occur. And just in terms of the mathematics, we usually have to deal with discrete random variables a little differently than we deal with continuous random variables. So in discrete random variables, we said most often we have a set of k different possibilities, and we have a probability associated with each of those. So it's like there's k specific marbles, there's a probability of drawing a given marble, with a certain value. And you stack all those probability values into a vector, and that's your probability mass function. Then we also talked about continuous random variables. For those, they take on any real number. So we can't just talk about a finite set of possible values. It's an uncountably infinite set of possible values. We can't talk about this vector of probabilities like that. We have to think about a function, and that's our probability density function. It is similar in spirit to PMF, but it's a whole function. And so it tells you the probability density as a function of the real line. And what we need is that function integrates to 1 and it's non-negative. Other than that, it can be anything. So, and everything we're talking about here is summarized in this document I wrote that tries to go through all these basic concepts. Okay, so we don't need to know a huge amount about random variables for this course. We essentially just need to know how to deal with expectation. Expectation is just another word for the statistical average. So let me just enforce that by saying statistical. So we learned in Unit 1 about a different kind of average, which if you have just a list of numbers and you want to average that list, you just add them up and divide by the number of elements in the list, right? That's the sample average. That you do on just raw numbers that are not random. This is the statistical average. This only works on random variables. Conceptually, it's very similar, but the details are a little bit different. So essentially, it's like saying I have this big bag of marbles, and I want to know what happens on average when I pull marbles out of the bag. Okay. That's what it's talking about. It's talking about that random variable. Okay, so if we want to write down mathematically exactly what this is, let's write it in a little bit more general form than just the expectation of a random variable A. Let's write it as the expectation of some function of that random variable A. So that function could be like squaring, for example, if you want to think of a concrete example. So when we have a discrete random variable, what we do is we basically look at the function applied to the kth possibility of that random variable, which we wrote with A sup k, times the probability of drawing that kth possibility, and then summed over all the capital K possibilities. So that's what it would be for a discrete random variable. And for a continuous random variable, basically we just replace the sum with an integral. So we have an integral from minus infinity to infinity of the function of this dummy variable A, which is just the variable of integration. And then we have our density, P sub A. The big A is the name of the random variable. And then inside that density, we access it with this dummy variable A, and then that's our variable of integration. So we have a dA. Okay, so these are just the basic definitions of expectation. If you're ever wondering, how does expectation work? You can just come back to these definitions, and then it's just basic algebra and calculus. And probably you guys are either really familiar with this stuff or really unfamiliar, like it's very rusty. And me talking a lot about this is not going to change either of those. So I'm going to leave it up to you guys. If you need more practice with this stuff, more refresher, then please do take a look at this document, study it on your own time. But I will tell you just a little bit more about specifically what we need to know about how expectation works. We really only need to know two key properties of expectation, which is the linearity property and the independence property. And so this is how it goes. So I'm going to write random variables with capital letters A and B, and I'm going to write deterministic variables, non-random ones, with small letters. And so let's say we're doing this. We're looking at the expected value of a deterministic constant plus D, which is a deterministic scaling of a function of a random variable A. So what happens when I take the expectation of this? How many of you guys feel like you know this? Okay. How many of you feel like don't really know? Okay. Okay, it's fine to raise your hands. I like to know these things. So, but this is super important. So, pay careful attention. Please, go back and read this. This is super important. This stuff is definitely going to appear on midterms, as well as the homework. You'll get some practice on homework 3, but you'll be tested on the midterm on this stuff. Okay, so what we would like to do now is do this expectation. So the first thing to remember is that expectation is linear. So the expectation of this sum of two quantities is the sum of the expectations. So we can look at the expectation of C individually and add that to the expectation of this second term. Okay, so that's linearity. Now we can go a little farther. What is the expectation of a non-random thing? It's just that thing, right? C. So that's the first term. It's C. And now we're going to get the expectation of the second thing. So what can I do with that D? I can pull it out of the expectation because it's just going to scale that whole expectation. So that's, again, the linearity property. So I'm going to have D times the expected value of whatever function of A we are working with. And I can't really simplify that last step at all. I need to know exactly what the function is. I need to know what the PDF of that or PMF of that random variable is. In other words, I need to do this stuff. So this is pretty much as far as I can go to simplify it. But as you can see, there is quite a bit of simplification. We're going to use this a lot later today. Any questions on this linearity property? Okay. The next one is an independence property. So let's say we have these two different random variables, A and B. So we're going to assume, so if we assume that they are independent, so what does independent mean? So we'll talk about this a little bit more on the next page, but when you have two different random variables that are possibly connected statistically, you want to think of them together. You don't usually want to think of them as separate. It's because that's kind of ignoring what happens in common between them. So when we work with them as a pair, we actually can talk about this joint probability mass function. It's very similar to this guy we talked about here, but it works on both of them together. So when we say that we have two random variables that are independent of each other, what that means is that you can rewrite this joint probability as a product of the first times the second individual probability density functions. That's what independence means. If the variables are not statistically independent, you cannot break this down this way. You just have to leave it like this. Okay, so that's what we mean when we talk about statistical independence, that you can break the PMF into a product of two independent PMFs, or two decoupled PMFs. Okay, so now that we have independence stated, if A and B are independent, then it turns out that any function of A, we can think of that as a new random variable, will also be independent of any function g of B. So now I have the expectation of, again, two independent random variables, the product of them. It turns out that I can write that as the expectation of the first times the expectation of the second. So this is an important simplification that we can do if and only if A and B are statistically independent. Okay, so these are really almost the only things we need to know about expectation, but we need to be able to work with this and be good at it, be able to recognize this when it appears and work with it. Okay, any questions on this stuff? So yeah, with these like kind of simple identities, you can derive tons and tons of stuff, and we'll see that moving forward. Okay, so now making it a little bit more complicated, we need to also talk about something called conditional expectation, which is basically the mean value of this function of random variable A, given that some other random variable B takes on a specific value B, little b. Let me give you an example. Maybe the random variable A is it describes whether it's raining in Columbus, Ohio or not. So you might say, okay, if you looked out the window at any moment of a year, what's the probability that it's raining in Columbus? I don't know, maybe 1 in 100, okay? That would be if you just looked at the average value of this. So let's say 1 if it's raining, 0 if it's not, then the average value of A, whether it's raining, is 0.01. But now what if I told you, how often do you find that it's raining given that it's sunny outside? That's a very different value, right? Because there's a connection statistically between when it's sunny or not and when it's raining or not. So that's how you can kind of think just intuitively about what conditional expectation is. It's asking, what is the average value of this statistically given that some other statistical variable is in a certain state? Okay, so how do we define this guy mathematically? It's quite similar to what we did on the previous page. We have an integral. We have that function of A. And then we just write this thing, which is the conditional probability density function. Okay, so this is conditional PDF. This is like the PDF of A, given that random variable B, capital B, takes on the value little b. So hopefully that's tangible enough. Yes?
So is that an f of little a?
Oh, yes, thank you. That should be f of little a. Thank you very much. Okay. Okay, and so again, if you ever have a question about conditional probability, you're like, does that work like this or like that? You can come back to this definition, just plug stuff in, and use algebra and basic calculus and answer your question. So you'll have some examples of that on the homework.
Sorry, I might have missed this. Why do you have like a subscript A dependent on B, but also the parentheses A dependent on B?
That is a great question. So these guys are the random variables, the big bags of marbles.
Okay.
These are specific numbers. The specific number A is the dummy variable in integration. It's just like you're looking for the area under this curve, and you're just like sweeping A through the real line. B is the specific state that the random variable B is in. So like random variable B might be whether it's sunny or not. Little b is sunny. Does that make sense?
Yeah.
Okay. But yeah, that's a great question, why we have all this notation. These guys remind us which random variables we're dealing with, and these are the specific numbers we're plugging in to evaluate that function. Okay. Great question. Any other questions so far? Okay, so let me ask you this question. This whole quantity here, is this a random quantity or is it a deterministic, a non-random quantity? What do you think? It's deterministic. It's going to be some function of little b. We could write it as like g as a function of little b, just if we wanted to give it a name. It is not going to depend on anything else. It's just some function of little b. As the little b changes, I can draw out that function once I do whatever computation is required for this integral. Okay, great. So, but what if you see this expression somewhere? That is very similar, but it's missing this little equals b. So in this case, you are not fixing the value of random variable at little b, you're just letting it float and be random. So you could write this if you want, g as a function of big B. That guy, is that random or not? Yes, that is random because if b, capital B is random, and I take a function of something that's random, I get something else that's random. Okay, so that's the difference between this when you fix it at a particular value and this when you leave it random. It's not in any particular value, but it is this random quantity. And for example, you could then take the mean of this, and then that would finally be deterministic. Okay, in fact, yes, question?
You were giving an example to explain this concept, right? So let's say we try to bring it back to that example, saying that the probability of raining when it's sunny outside, that value is still going to remain randomly, right? It's not deterministic. Then how can we define that this function is deterministic now?
So if we leave whether it's sunny or not as a random thing, then
No, but the idea is to find if it is going to rain or not. That is still going to remain random, right? The probability of
sometimes we want it to remain random and sometimes we want to fix it.
My point being that, let's say the probability of raining is going to stay random, right? If we don't know that. So the probability of raining when it's sunny, although less, but it's still random, right?
It depends if we're fixing sunny or if we're saying it's sunny or not. That itself is random, whether it's sunny or not.
Yeah, that is a condition, but then the final thing which we're trying to predict is to understand if it's raining or not.
So yeah, it's a matter here. This is if you're fixing it being sunny,
Yeah.
and if you didn't do that, then you have to acknowledge that some fraction of the time it's sunny, some fraction of the time it's not sunny. And so if you then wanted to figure out, if it's raining on average, you have to consider both those possibilities, that it might be sunny or that it might not be sunny. So yeah, some of these things you just have to think about a little bit. So here's actually where we can, remember how we said we can think of this as random. So likewise, we can think of this as random. And this is random because essentially this expectation is really taking out the randomness in A, but it's leaving B be random. And then this outer expectation is really working on the randomness that's induced by B. Once we've done that, there's no more randomness. And the interesting thing is, this is called the law of total expectation. This finally gives us the expectation of A. So you can find a derivation of this in here. I'm not going to go through it now. But the way that this is typically used is if you have some expression of several things, and it's easy to take the expectation of one thing at a time, you can kind of take one at a time, then another, and eventually that's going to be the same as taking the expectation over all of them. So we'll see an example of this in a couple slides. Okay, so that's conditional expectation. It's the average given that something else is happening. So with that, we can actually bring things back to machine learning, and we can see why we're defining all this stuff. It comes back to trying to understand this bias this underfitting and overfitting. We know that underfitting is bad because it's too simple. We know overfitting is bad because it's too complex and you fit noise. But those are very kind of, I don't know, those are not very precise understandings. We want to be able to precisely say exactly why is overfitting bad, what is bad about it, and what is not bad about it. So that's where we're going. And in fact, for some simple models like linear regression, we can actually even compute expressions that will tell us exactly how overfitting affects us as our data set grows, as our number of features grows, and so on and so on. So this is how we're going to set it up. We're going to have a true model, and we're going to have a prediction model. So the true model governs the actual data, outside of us applying machine learning to it. So it says that the targets y are equal to some generic function applied to the features in a vector x plus some additive noise. And we're going to assume that that additive noise has zero mean, so statistically it's zero on average, and it has a variance of sigma squared. Oh, actually, that reminds me, I wanted to say one more thing about variance. So hold that thought. Let's come back to here. Let me define variance. So we learned about sample variance in Unit 1. Now let's do statistical variance. So we're going to say var of a random variable a is going to be the mean, statistically mean, of a minus its mean squared. Okay, so conceptually, this is exactly what we did before with sample averages, but now we're doing it with statistical averages. In both cases, you take the variable, subtract its mean, square it, and then take the average of that. But in this case, the averages are statistical averages, not sample averages with sums. Okay, so when we talk about statistical variance, this is what we're talking about. And there's one other very nice form of this, which is similar to what we did back in Unit 1 with the deterministic ones. We can write this as the expected value of the quantity a squared minus the expected value of the quantity a, that thing squared. We did the derivation of this for summations back in Unit 1. We call them like the alternative expressions. But essentially, you can do the same thing here with these statistical means. Okay. Any questions on this last thing? Okay, so coming back to our model again. In this model, we have to be clear about which things are random and which things are not random. So the noise, epsilon, is random. We're going to think of that as a random quantity. We're going to think about this vector of features also as random. The function f is not random. That's just a fixed thing. There's this true function. That's deterministic. But because x and epsilon are random, then y will also be random. Now, when we talk about epsilon, we're going to assume we don't have to know the specific distribution, like it might be Gaussian, it might be uniform, it might be whatever. It doesn't matter. But what does matter is that the mean is 0, statistical mean is 0, and that the variance is sigma squared. And based on that last equation that I wrote on the other page, you can also understand this to mean that the expected value of epsilon squared is sigma squared because the mean is 0. So because the mean is 0, these two things are equal.
So, my true model, that's saying, are we sort of saying this is what we ideally have?
This is how the data is generated. This is how the data is generated. So usually we go out and we collect data, and it looks kind of random. Maybe if I would have collected the same data on a different day, it would have had a lot in common, but it would have been just a different thing again. So what's the truth that underlies all those different days I could do a collection? That's this model.
Oh,
Does that make sense?
yeah.
Yeah. So this is like the statistical model where we're modeling things with random variables x, epsilon, the random variables, y is then random. And so we have to talk a little about independence. So we're going to assume that the noise, epsilon, is independent of the features. They are not statistically connected. Also, this model holds both for training and for test. So when we talk about our training examples, they were generated from this model. When we talk about, maybe finally doing some prediction on a test sample, that test sample and the true test label were also generated from this model. But we're going to assume that the training and test quantities are statistically independent. So basically, it means that at least for the x's and the epsilons, those are statistically independent in the sense that if I have certain training things, training x and training epsilon, those are statistically unrelated to what happens at test. Okay, so that's the truth. What about the prediction model? So this is what we design.
Yeah, I guess that was another question. So if we're immediately setting the expectation of error to be 0, why do we have the error in the true model in the first place?
Oh, this is at 0 on average, but every time you observe it, it's maybe never 0. Like maybe sometimes it's a Gaussian, let's say. So sometimes it's negative, sometimes it's positive. So it's non-zero, but on average, it's 0.
Okay.
Does that make sense?
Yeah.
Okay.
So why is the variance supposed to be sigma squared? Is it like?
It's just a notation.
Okay.
Yeah, it's just a common notation for sigma squared, or for variance. Okay. Okay, so this is our prediction model. This is something we make up. We're going to call it f hat. Generally speaking, f hat does not agree with f. It might, but usually it doesn't. Also, our f hat depends on some parameters, beta, that we need to figure out. The way that we figure them out is we learn them from a training set. So there's some training set, and that's where you see the i's. These are our training targets and labels. We assume that our beta hat was designed from that training data. For example, we know how to do this with linear regression. We can use the same generic procedure for a lot of other things. You zero the derivative, et cetera, but we'll just assume that we have designed the parameters of our model from some training data. But here's the thing. We are thinking about that training data as random. And because the training data is random, then these prediction coefficients should also be thought of as random. So let me give you an example. There's some Python code for this unit that generates that polynomial curve. It generates some random samples x, some random noise, gives you random targets. Every time you run the code, you get a different set of numbers, right? So each time you run the code, that's a realization, but if you can run this code over and over and over again and get different numbers every time, and so there's really some random variables underlying that code. And those random variables have certain means and distributions and so on. Okay, so that means that if every time I run the code I fit my feature vector beta, I'm going to get a different beta vector every time because my training data was different every time. So that's why we can think of beta hat as random. Okay. So basically, we have this random beta hat. We have a fixed deterministic function f hat that we've chosen. And then that's going to give us some, random targets y hat. Okay, we'll see some pictures of this in a couple slides that will make this concrete. So, any questions so far on the model? We have a true model for the true data. We have a model for how we make our predictions. Any questions so far? Okay. So now we have to measure. What do we consider error? We're going to focus on mean squared error, just because it's really nice and easy to work with. So by mean squared error, we're going to look at the difference between the true target and our prediction squared. But we're actually going to do this by fixing the value of x. So we're going to say, and you can think of this x as the test x. So at test time, someone is going to give you an x. They're going to know what y is. They won't tell you. And you're going to try to predict it with y hat. And this is going to measure for that x how good your prediction is on average. Maybe they ask you to do this experiment 100 times. So you're kind of talking about what happens after those 100 times you've done this experiment. But that's this mean squared error. And you're measuring the mean squared error on y hat, but you're making this a function of x. So as x changes, your mean squared error changes. Maybe for some x, you do great. Other x, you do terrible. So that's what we're going to analyze. We're going to analyze this, and we're going to boil it down to 3 important terms that are going to be very meaningful. So, any questions, or are we ready for the big derivation? All right. So bear with me on this. It's really not bad, and actually, this is good practice for all that expectation stuff. So, and this is finally, at the end of the day, like I said, one of the most important equations all semester, if not the most important. So, this is what we're starting with. We want to analyze the mean squared error on y hat as a function of a specific test vector someone is giving us at test time. So, according to our definition on the previous page, this is what it is. We also have some definitions for the true model y. That's just this. We're plugging that in. And we have our definition for our prediction y hat. That's just this. So we plug that in. Okay. Everything so far so good, right? So now let's think about this. Let's think of this. Oops. Think about this term as one thing and this term as another thing. And let's think of it as a quadratic, a square of a sum. So we're going to expand this quadratic into the first thing squared plus the second thing squared plus the cross product. So the first thing squared, this is all inside this expectation. The first thing squared is just epsilon squared. The second thing squared is over here. And the cross product is just 2 times epsilon times this. Right? So far, so good. Just basic algebra. Okay, so now we can start using our linearity of expectation and independence. So I have an expectation of the sum of 3 terms. We know, because expectation is linear, that I can write that as the expectation of the first plus the expectation of the second plus the expectation of the third. So that's the linearity property of expectation. So here you can see I get expectation of the first, I have expectation of the last, and I've done a little bit of simplification that I'll describe in a second, but this is expectation of the cross term. So let's talk about that middle term. So again, I'm looking at the expectation of this. So I have that 2 in front. 2 is deterministic. I can pull it out, right? Now I have the expectation of this thing times this thing. Here is where we need to consider whether those 2 things are independent statistically. If so, I can look at the expectation of the first and multiply that by the expectation of the second. So again, is our test error independent of these other things? These other things are random because they depend on the test features and they depend on the training parameters, which are a function of the training data. So yes, this epsilon is independent of this other stuff because, number one, we said that what happens at training time is independent of what happens at test time. So this beta hat is definitely independent of this other stuff. And also we said that the error is always independent of the features. So as a result, this epsilon is statistically independent of all this stuff, which means when I look at the expectation of the product, I can write that as the expectation of the first times the expectation of the second. Is everybody good so far? Okay, so now we can start to simplify. We need to look at this, expectation of the noise given the features x. So it turns out that if these two things are statistically independent. In other words, the features x do not have any bearing statistically on the noise, then I can pretty much ignore this conditioning when I take that expectation. So now, really the right way to do this is to write out a few lines, go back to the definition of expectation. You can prove that this thing equals expectation of epsilon because x is independent of epsilon. So that's actually a good exercise for you to do. I'm not going to do it right now. But once you do that, we're almost done because we remember that the expectation of epsilon was 0. So that means that that term vanishes and means that this whole thing vanishes. So it's gone. Okay, how are you guys doing so far? Making sense?
But I guess I'm not sure what that would mean for like a real model. Like, does that not matter?
Yeah, we'll talk about what it means in terms of the real model when we get to the end.
Oh.
But yeah. So yeah, I think that's probably what's best to focus on. Okay. So again, we used linearity to do this, and we also used the statistical independence of epsilon and beta hat to do this factorization here. Okay, so now, yes?
So, just to clarify, what is x in this one?
So x here is going to be, we can think of them as our test features. So at test time, there's going to be a true label, y. There's going to be our prediction, and we want to know like what's the average squared difference between them. If I have done this experiment many, many times and I look what happens on average. Every time I've done this experiment, I'm going to have different training data. I'm going to have different training noises. You know, that's what's going to change. But what's not going to change is I'm fixing my test features x. I'm holding that fixed.
So, when you're saying features, I thought since this is a common vector, it would be the samples of one feature. Is that not the case?
That's not the case. So x for us is always like all the different D features.
Oh.
And when we talk about samples, we always have a little I on it. So like the ith training sample would be an entire vector x of D features. But this is actually just, I'm thinking about this as my test, not training, but test feature. Because what I really care about, I don't really care about what happens at training. I want to make sure that the model I design is actually good at later, once I'm done training, when I apply it to test data.
But this is one feature, right?
So these are all the different features
Okay.
in X, yes.
So expected value of epsilon given x and expected value of epsilon, they are all same thing.
You can prove that they're the same because X is statistically independent of epsilon. And that's a great exercise. You can do it in like 3 lines, but it's a good exercise. Go back to the main definitions of conditional expectation and independence, and you can get it. Okay, so our next task is to simplify this plus this. Okay, actually this first one, we can handle this pretty easily. So here again, because x is independent, for the same reason, this is equal to the expected value of epsilon squared without the x in there. Because x has no bearing on what happens with epsilon squared because it's statistically independent. But again, you can derive this from first principles. So this one, do you remember what this is? We actually said that this guy was sigma squared. That's just a number. We're going to plug that in over here. Okay, so that leads us to that sigma squared just ends up being here. And that means that's really the thing to focus on next is simplifying this. Okay, so we're going to do a little trick here. We're going to add and subtract the same quantity, which is nothing more than sticking in a 0. Right? And unfortunately, I meant to put a condition on x in this expectation. I just uploaded some revised slides that have that fixed, but it's not a big deal. Just remember that these are all conditional expectations. Every single one of them has given x. Okay, so So what we have here is we have f and then minus this thing plus that same thing and then minus f hat. Okay, and now what we're going to do is we're going to do another one of these expanding the squares, but we're going to think of this as the first term and this as the second term when we expand this square. So that's going to give us this quantity squared, which is here, this quantity squared, which is here, and then the cross term is going to be that last long term down here. Okay, let's handle this one first. So let's take a close look at this stuff inside the square. Is f of x random or not? Is it deterministic or random? It's a little bit of a trick question. So generally speaking, we think of x as a random variable. So generally speaking, it should be random. But because of this conditioning, we're saying we're fixing x at a particular value. Because of that, this becomes deterministic, or actually because of this one here. Right? Okay, so because I'm fixing x at a fixed value, we can think of it as deterministic. Okay, what about this thing? Is this deterministic or random? So there's two sources of possible randomness, x, which we said actually we're fixing, and then there's this beta hat, and that is really what this expectation is applying to. Expectation is really going over our training parameters. So this expectation is removing all the randomness due to the betas. As a result, this thing we're left with is deterministic. So what that means is that all of this is deterministic, which means that this expectation is useless. Just get rid of it. So down here, we have that same thing, but without the expectation. Okay. What about over here? Okay, actually, all we're doing to go from here to here is we're just swapping the order. So we're just making the notation a little different. We're actually not really simplifying it. I just wrote it in a way that's a little bit more common. All I did is, because there's a minus and you're squaring it, I can swap which one I do first, right? So not really simplifying that. We'll talk about it. We'll interpret it in a moment. But then the last thing is the cross term. It's this thing times this thing inside an expectation. So to navigate that, we have to remember that that first thing is actually deterministic. So I can move that expectation through and apply it only to the second quantity here. Right? So I move that expectation through because all this stuff is deterministic. Does everybody go to that? And then the very last thing we have to do, and then we'll be all done, is figure out what is this. So there's a couple ways to think about this. The more mechanistic approach is to say, well, let me just distribute this expectation. I'll take the expectation of this. Well, this is deterministic, so the expectation of that, I can just have this without two expectations. And then I have expectation of this. Well, the expectation of this f hat is exactly what this is, so that this minus cancels them and they disappear. So that's why this goes to 0. Another way you can think about it if you want is you can say, this is some random variable. This is the mean of that random variable, so I'm now looking at the deviation from the mean. And by definition, the average deviation from the mean is 0. So that's another way to think about it. In either case, this whole thing goes to 0, which means that this last term disappears.
So is the beta hat not a random variable? Is that why it's deterministic?
It is random. So where is that worrying you?
What is that?
Where is the randomness worrying you? Beta hat definitely is random.
The f hat x semicolon beta hat.
Here? Yeah.
Yeah.
So because this is a random variable, this expectation is like averaging out the randomness due to that beta hat, if that makes sense. But it's not averaging out the randomness due to x because we're fixing x. Okay. So we're finally done. We have that the mean squared error can be written as a sum of 3 terms, and it turns out that all of these terms are important conceptually. The first one is called the irreducible error, And it's named so because in a perfect world, you could possibly set the bias to 0 and the variance to 0, but you would never be able to reduce this. And this is a positive quantity. These are all positive quantities. So basically, this is the lowest possible, the best possible you could do in your mean squared error. And it's kind of like saying back to here, if your prediction model was perfect, you could perfectly predict this, but you will never be able to predict this epsilon because this epsilon is generated independently of everything else. So there's no way to predict it. So that will be there, and finally, that will give you an error, sigma squared. That's where this comes from. Okay. The next term is called the bias. So let's look at it. This is the difference between the true noiseless model. Remember, the true model actually has noise in it. So when you look at this alone, you could say that's the true noiseless model. You could also say that for a fixed x, this alone is the average. What happens on average if you fix x? Because when you average out this epsilon, it goes to 0. So we can think about this as noiseless true, or we can think about it as the average truth for a given x. This one over here, a little bit easier to interpret. This f hat, remember that's just our prediction model. This is just y hat. It's a fancy name for y hat. So what that means is this last term is this is the average value of our prediction for a given x. So average value of y hat for a given x. So this difference between the truth and our prediction on average is the bias. So what happens is it could be that, our prediction is never perfect. It's always different than the truth, but on average, it's correct. We would call that an unbiased model. Now, something else could happen where we're never correct, but on average, we're even off. Maybe we're too big on average, too small on average. That would be a biased model. So bias tells you how good your prediction is on average, and in this case, for a given x. Okay, everybody good with that? So that's bias. So irreducible error, bias. And finally, the last one is what we call the variance on our prediction given x. And when we look at this, you can see we don't really have the truth in here. This is our y hat, and this is our average y hat. So this is not about how good our model compares to the truth. It's about how much our model fluctuates around its typical value, its mean value. So this is the mean value of our y hat, and this is the actual value of our y hat. And if you remember, variance is like variance of y is y hat minus mean of y hat, quantity squared. So this would be the variance, but it's a particular kind of variance where we're just fixing x. So it's the conditional variance. Okay. So I'll show you some pictures on the next page, and I think everything will make a lot more sense once we see the pictures. But it says that the MSE can always be written in terms of these three terms, and as we'll see, they all play a fundamental role. Any questions so far? Yes.
So, in the earlier line, you said that basically, if we average out the variance and its difference with mean, it will be 0. So that's why this is.
So this here is y hat. This is the average y hat. And so when I look at the squared difference between y and its mean, that's where I get the variance. I'm not sure. Above here?
Yes.
Okay. Yeah. So here you could say I apply this to this, and it's redundant, so nothing happens. I apply this to this, and I actually get this. So then when I subtract them, they cancel. Make sense? Okay. Okay. So all of this analysis we did here was for a fixed x. And you might say, well, I don't really care what happens in practice with a fixed x. I want to know what happens in practice like over all the x's I'm going to see. Or, I actually care about the x's that are going to happen most frequently. So you might say, okay, I actually want to take an expectation over x. And then I get the MSE that's not conditioned on x. I just get the plain MSE. How bad is y hat on average? So here I'm averaging over all the possible x as well as everything else. And in that case, we just look at the expected value of this, which doesn't change. We look at the expected bias. Actually, this is a squared bias. Let's not forget about that. It's a square on the bias. So we get the expected squared bias, and finally we get the expected variance. So just to remind you, really this expectation is applying, it's taking out that randomness due to the x. Okay, so sometimes that's just a single number and you just want to know that single number. You don't actually care to know the bias at specific x's or so on. Okay, so this is the big nasty derivation, and now I think this will help put everything together, these pictures. So we're back to our experiment in Python, and if you remember in that experiment, we had a true model, which was this cubic function here as a function of x. So x is on the horizontal axis, and y is on the vertical axis. So the true y is this red curve, and in this first case, I'm looking at d equals 1 when I do my model. That's a linear model, so I'm going to get a line, right? Every time I run this experiment, I'm going to get a line. But every time I run an experiment, the line is going to be a little bit different because my training data is always generated randomly. And so my line it shifts up and down, it tilts a little bit. It's never going to be the same. So if I want to summarize it, I can say, well, what is the line on average? If I average over all those shifts and tilts of the line, that's this green thing here. The green solid thing, the green solid line, that is the average line. If I want to know the deviations from the average, that is what these little error bars are showing. So you can see how much that line wiggled around as I did all these experiments. I did 100 experiments to make these curves. Okay, so every time I use slightly different data, my line moves around. But this is what it is on average. Okay, so now we can talk about the bias. What is the bias? The bias is the difference between my average model, which is that green line, and the average truth, which is the red curve. So the solid green curves show us expected y hat given y, and the bias is the gap between the red and green curves. So it means that for this particular x, let's say 0.5, the bias is the gap there. That's the bias for 0.5. If I want to know what is the bias when x is 0, well, I got lucky. It's actually 0 there. But you can see now why bias depends on x. Because depending on what x is, I have a different size average difference between truth and prediction. Everybody good with bias visualized? Okay, what about variance visualized? Variance, we said, is how much the predictor deviates from its average value. So the average value of my prediction curve is this green line. So if I want to say what is the average value at 0.5, then that would be exactly this point right here. Now if you say how much does my prediction vary around its average, I'm showing that with these error bars. So that's how much the line wiggles around relative to its average value. And you can see there's a little bit of wiggle. It's not so bad, but it does actually change a little bit because my training data is always a little different. So my line is always a little bit different. So that's variance. So the green error bars show us the variance of y hat given x, for a specific x. Okay. Everybody good so far? So let's see what happens when we increase our model order to 3, which remember that's the true model order. So what you see here happening is that all of a sudden there's no bias. My green curve is sitting exactly on top of my red curve. So on average, my prediction is correct. But that does not mean if I were to look at any specific experiment that it's correct. The specific experiments actually have green curves that are moving up and down. They're all cubics, but they're shifting up and down. And so I can show how much they shift up and down at any given x by those little error bars. Okay? So we're getting to the end here. So what happens if I use d equals 14? That's a huge model, way more than we need. And what you can see here that's interesting is there is still no bias. On average, that model is always working perfectly. But what's happened is that the error bars have grown much larger. That's where we're going to have in trouble. So it's like, on average, those weird 14-order polynomials are they're quite a bit different from their average value. And in fact, we can skip back earlier. We have a picture of one of them. Here. Okay, this is d equals 15, but it's almost the same. So you can see how for this particular experiment, we actually had this crazy curve that went like this. Well, if we would have done this experiment 100 times and averaged all those crazy green curves, basically they would line up almost perfectly with the red one. It's kind of cool. That's what happens. Okay. So hopefully these pictures help to crystallize the meanings of this bias and variance. And here's a cartoon on the bottom that's very, very useful, just really simple terms. Let's say you're throwing darts at a target, and let's say that someone says you have high bias and low variance. That means that on average you're far from the target, but you're very consistent. You have a low variance around where you usually land. On the other hand, they might say, well, what if you have no bias, but you have medium variance? That's like, on average, you're perfect, but you have you're not always hitting the target exactly. You have some variance around your average. And finally, here we have no bias, but high variance. That's, on average, you're doing perfect, but you have a lot of variation from the average. So you can see that, this, in terms of mean squared error, that's like how far are you from the target squared on average. This has the best mean squared error, right? This has worse mean squared error, not because of variance, but because of bias. And this has worse squared error, not because of bias, but because of variance. So bias and variance are different bad things that can happen. And ideally, we want to minimize both. But it turns out that's usually not possible. Usually, we have to trade off between one and the other. So let me just show you the typical way this works. So here's a typical curve of, as your model gets more complex, what happens is your variance increases, and that is what kills you. On the other hand, if your model gets simpler, then your bias gets worse, and that's what kills you. And you usually want to find somewhere right in the middle, which is best balancing your squared bias and your variance. And your mean squared error is going to be the sum of those plus the irreducible error. And that's this. So we really want to maybe minimize mean squared error. So we have to do the right job of trading between bias and variance to get the best trade-off. So is that kind of making sense? How we did the decomposition and what the things mean now? So as we go through the term, we're going to keep referring back to this idea of, well, if you do that, that's going to increase your bias. If you do this, it's going to increase your variance. And so really you want to trade off. So that's kind of a lesson. I don't want to take much more time, but next time we'll talk more about, we can actually, for least squares linear regression, we can be much more specific. We can even derive an equation for the variance in specific numbers and stuff, but I'll hold off on that. We're almost done with this unit, but just have a little bit more. Okay, have a great weekend. See you on Monday.